Sandeep, so I don't know if how many of you were here last year for a similar event. It was amazing, and this as event is unfolding, I can see that it's amazing. So thank you, Sandeep. All right. So with that, let me start by introducing my my co-organizer, Aditya. So Aditya, first and foremost, he shares the same alma mater as myself. There's IIT Bombay, so really glad about that part. He is a professor with statistics and data science, as well as machine learning at Carnegie Mellon University. At Carnegie Mellon, he received his PhD, where he got the best thesis prize. After that, he had a few years at Berkeley in statistics department, and now he's back at where he started. And I'm looking forward to part one of his talk today. We'll have enough time to brew it over during the rest of the evening, and then we'll come back with the part two of the talk.
Okay. Thank you very much for the introduction, Devavrat. And I second what he said about Sandeep. Thanks a lot for helping with a lot of the groundwork at the IFR. It's been amazing being a co-organizer because it was so easy. You made it very easy for us. So thanks for making it to the afternoon talks. I know after lunch the temptation can be to snooze. I'll try to make that as hard as possible for you. So this work is about uncertainty quantification for black box models. So black box models have become very popular in machine learning, and of course, random forests boosting things like that maybe a couple of decades ago. But more recently, neural nets have regained popularity, and so those are examples of black box models. And what we'll try to do here is provide uncertainty guarantees for such black box models without making any assumptions. Okay, so this is a recent line of work, maybe 2 or 3 years now that I've been thinking about this and working on it. A lot of it is with my 3 collaborators, Reena Feugl-Barber, Emmanuel Candes, and Ryan Tibshirani. We call ourselves the Baccarati group. This started at AIM, which is the American Institute of Math, where a few of us can get together year after year to work on a series of problems. And everything I'm going to talk about today stems from work with them, and each one of them has opened my mind in very different ways, and they've been amazing collaborators. Some of what I'll talk about tomorrow will be joint work with 2 younger students. Arun is graduating from Wharton this coming semester, and Chirag is one of my PhD students at CMU. Okay, so a quick outline. First, I'm going to talk about what does the term predictive inference mean. Everyone in this, hopefully everyone here is familiar with the concept of prediction, but what is predictive inference? And then, once we set the stage of at least understanding what is the aim of this talk, we look at some methods for assumption-free predictive inference, and that will form the bulk of today's discussion as well as part of tomorrow's. And then we'll go up into some empirical observations of how these perform in practice. We'll look at some generalizations. I'll start off with a simpler setting and then generalize it later. And I'd like to end with some open problems. There's plenty of open problems in this area, and some which I think are important and summarize. So it's going to be 2 lectures, one today, one tomorrow. Okay, so let's jump right in. So what do we mean by predictive inference? Okay, so this is prediction. You have some training data, some set of points that are given to you, let's say, denoted x1, y1, and xn, yn. Now, x lies in some space. It doesn't have to be a Euclidean space, but for simplicity, if you want, you can think about it as RD for some d-dimensional space, but it doesn't have to be. Y does not have to be a real valued, like you're not doing a real valued regression. Y could lie in any space, for example, a metric space. But for simplicity, you might want to think about Y as being a real value. That's your label that you want to predict. So you're given training data of this kind, x1, y1 to xn, yn. Let's say they come from some joint distribution pxy. Okay, so this is prediction. There's a new point, xn plus 1, coming from the same distribution over x, px. And I would like you to predict yn plus 1. I would like you to predict its label. Okay, so that's the prediction problem. And usually, in order to solve this problem, what we do is we employ, this is working, there. We employ an algorithm. Okay, this algorithm is often, random forest, linear regression, something of that kind. An algorithm, the output of the algorithm is a predictor. A predictor is just a function from x to y, so that when you evaluate the predictor at xn plus 1, it gives you its prediction for yn plus 1. That's a predictor. And an algorithm is something that produces such a predictor. And so an algorithm is something that takes in some set of points, some set of endpoints, and outputs a predictor. Okay, and so this is what I mean by, for the rest of the talk, this is what I'm going to mean by an algorithm. It takes in a data set, outputs a predictor, and a predictor is what I'm going to use to do my prediction. Okay, and so I'm going to use this predictor, and I'm going to predict a of xn plus 1. That's going to be my prediction. That's what we usually think of as prediction. Okay, so what is, if this is prediction, what is predictive inference? Predictive inference is saying, I don't want just your prediction. Your prediction alone is not useful to me. What I would like is some uncertainty quantification around your prediction. What I would like instead is a set C of xn plus 1, a confidence set, that's why it's C, or a conformal set or something of that kind, such that the probability that yn plus 1 lies in that set is at least 1 minus alpha. Okay, so I'm not looking for just a point prediction, I'm looking for a set. Of course, if y is real valued, then that set might be an interval. It might be a union of intervals. It could be any such thing. If y is in some other space, it's just generally some set. And so the question is, I don't just want one point. I want you to tell me with high probability your observation will lie in this set. Okay, and so that's the difference between prediction and predictive inference. So inference is the term we often use for quantifying uncertainty. And so that's what I'll use over here. Okay, so alpha is going to be some number like 0.05 if you want a 95% interval. And yn plus 1, as I said, doesn't have to be real value. So this is not necessarily an interval. It's just some object and this is just some set. But for simplicity, think of this being an interval and this being a real number if that helps you. Okay, so why do we want predictive inference? Like why I mean, a lot of us might have taken machine learning courses. We have never come across this term predictive inference, and probably, you might wonder, why do we even want something like this? So it's easiest to think about an example. Okay, so let's say you ask the question, you're trying to predict how much time it takes to go to the airport, that's y, at some time of the day, x. Okay, and so maybe you have a bunch of data like this. At 3 a.m. it took you this amount of time, at 8 a.m. it took you this amount of time, and so on. So you have data of this kind. Now I ask you at 3:45 p.m., how much time is it going to take to get to the airport? Okay, and so now if you tell me, it'll take 80 minutes to get to the airport, that's not very useful for me to actually act, because 80 minutes plus or minus 5 minutes means something very different from 80 minutes plus or minus 40 minutes. And the way I will actually act as to what time I actually leave will differ a lot if you told me that that's your level of confidence for 80 versus that's your level of confidence for 80. So both of them are centered at 80, or both of them mean prediction is 80, but I will act very differently if in these two situations. And so this is something we find intuitive on a daily purpose, is that, we want to know how sure you are about the thing you're saying, but somehow in machine learning we drop this. We're happy with mean predictions. And so, but my claim is that that's okay maybe when you're doing cats and dogs, but ultimately when you want to make real world decisions, when you finally want to deploy machine learning in the wild, then we are going to need to quantify uncertainty of those predictions to make decisions based on those predictions. So in some sense, machine learning or prediction is never the end goal. In some sense, it's the first step on which you want to take some decisions, and then that decision making will be based on how certain you are about those predictions. Okay, and so I think that eventually I think we will mature to realize that we don't just want yn plus 1 as a point, we want a set. We want both a point and a set, something of that kind. And so the way we're going to quantify it is a high probability set. Okay, so that's predictive inference. Now, many of you might have heard the term confidence interval. Okay, and so I want to contrast a prediction interval from a confidence interval. They mean two completely different things. They're applicable in two completely different circumstances. And it's important to get that out of the way, because what I'm looking for is not a confidence interval, and I'll tell you why, what the difference is. So as I said, for a prediction interval, or a prediction set more generally, what we start off with is a prediction algorithm, which takes in a data set, produces a predictor. Now, a prediction interval or set satisfies this kind of a guarantee, as we have seen before. Now, what is a confidence interval in contrast to this? Usually, you have an underlying parameter that you care about. There's some parameter space theta. Theta could be, multivariate. It could be a complex space, but there's some set theta that you care about. And what you have is an estimation algorithm or an estimator that takes in a data set as before. It doesn't output a predictor. It outputs a point in this set theta. Okay, And the confidence interval satisfies the kind of guarantee that the probability that theta, the output, is in my set Cn is at least 1 minus alpha. Now, the main difference over here is to talk about a confidence interval, we have to assume some model relating y to x. Usually this theta is something related to this joint distribution pxy. It could be the mean, it could be the median, it could be when I regress y onto x, what are the linear regression parameters. So to talk about a confidence interval, you need to assume some kind of a model that you parameterize by theta. And maybe the set that you care about is not all of the parameters, it could be a subset of the parameters. For example, you might assume that y is x theta plus noise, and I would like to get some confidence set for these parameters theta. But to talk about this, we don't need to assume any model. There isn't any model. You might assume a model to help you with the prediction problem, but the definition of a prediction set does not need to assume any underlying model. Okay, but the definition of a confidence interval needs to assume an underlying model for which you are producing a confidence set for those parameters. Okay, so there's a fundamental difference. There's another difference. One is that usually, even if things are well specified, then as you get more data points, as n goes to infinity, the volume of your set Cn will go to 0. You get more and more and more accurate estimation, and ultimately you'll be able to perfectly identify the point. You have typically, that's what we call consistency or something of that kind, that our confidence set size will shrink to 0 with the number of samples. But that will never be the case with a prediction set. In some sense, there is a lower bound on the size of the prediction set. The volume of Cn must, let's say in the real valued case, it's an interval or something of that kind. It's at least the smallest it can possibly be. In some sense, what an oracle would predict is it would look at the conditional distribution of y given x, and it would take a 1 minus alpha level set of that distribution, and that's the smallest it can be. In some sense, another way to view that in terms of predicting how much time it will take to get to the airport, it means no matter how much data I give you about the problem, I'll ask you how much time will it take at 3:45, and there's always going to be some inherent uncertainty. You're never going to be say it'll take exactly 80 minutes because I have 10 years worth of data. No, it's going to be 80 minutes plus or minus 5, or whatever that is. There's going to be some amount where you just can't get beyond that amount, and your prediction, there's some noise essentially in the problem that you can't account for, which is in the distribution of y given x, and so the volume of any prediction set as n goes to infinity will never shrink to 0. And so there's just some fundamental difference between these two. It's good to keep it at the back of your mind that producing prediction intervals is a different task from producing confidence intervals, and the prediction intervals will have different properties from confidence intervals and so on. So in some sense, things you know about confidence intervals, just leave them aside for the moment, and the task of producing prediction intervals will be very different, and the methods we propose will be different. Okay, so any questions about the setup, about the goal, and so on? Yeah. Yeah. It's excellent. Yes, that's exactly right. Yeah. And in this probability statement, it's over the n points that you have because there isn't an n plus first point. Yeah, that's right. Okay. So if everyone's good with the goal, then now I'll tell you what in the title of the talk, there was this term assumption-free. Okay, and so I'll tell you what I mean by assumption-free. In general, I don't like assumptions, so here you'll see that we'll really not try to make any assumptions. So here's the statement of the problem. There are some blanks, but I'll fill them in. So here's the statement. I'm given data, training data, x1, y1 to xn, yn from a joint distribution, and I'm given a test point xn plus 1 from the same px, from the same x distribution, and I need to produce a set c of xn plus 1 such that for all distributions pxy, okay, so no matter what the distribution might be, the probability that yn plus 1 is in c of xn plus 1 is at least 1 minus alpha. So the most important thing over here is this statement must hold for all pxy. Not suppose pxy is the Gaussian, suppose y is x beta plus noise, suppose, no, nothing, don't suppose anything. Pxy could be arbitrary, it could be heavy-tailed, it could be non-smooth, it could be funky, it could be anything. And yeah. Yes, absolutely. Yeah, that's right. Yes. C is a function of, this probability is over all of the n data points, and C is, C hat or Cn. That's right, yeah. Yes. Absolutely right. Yeah. So that's the other side of the thing is, of course, you can always output the whole space in which you're done, but implicitly, whenever we ask for a confidence interval prediction interval, any of these things, we want this, but we also don't want it to be too large, and we will see that we can achieve that. That's right. Okay. So the most important thing is there's no assumptions on pxy. Now, as I said, often when we are doing prediction, we employ a prediction algorithm. We employ this statement over here. The statement of what I'm trying to achieve is independent of any algorithm. I haven't specified any algorithm here. I just said I have some data, I have a new point I want to predict. Okay, I want a prediction set for that point. But often we like to use an algorithm that we think is well suited to the data. We think that, okay, maybe for this particular data set, quadratic regression is a good idea, or for that particular data set, a convolutional neural net is a good idea. Fine. So if you... Yes, yeah. So that's the data is coming. That's right. The data is coming from pxy. Now, yeah. So for now, let's assume that they're IID. In the actual statements, we'll see we don't even need that, but we'll just need exchangeability. But let's say for now they're IID. Yeah. Okay. So we often use an algorithm to help us, and then what I want is that whatever algorithm you choose to use, this statement must still be true for that algorithm. So for any algorithm you might choose to use, this might be a smart algorithm or a terrible algorithm, but no matter what algorithm you use to use, for all pxy and for all algorithms you might choose to employ, this statement will be true. So what's going to happen is, when you see a data set, you're going to make some modeling assumption or you're going to make some guess of which algorithm is good for this particular data set. The final set that I produce should not depend on whether your algorithm was right for this data set or not. Okay, so maybe you make an assumption that y is a linear function of x. I want this statement to be true irrespective of whether y was a linear function of x or not, and irrespective of whether your algorithm was good or not. Maybe you used a ridiculous algorithm, maybe you used a smart algorithm. This is going to be correct. What we're going to see later on is that there is some sense of adaptivity, which means that if pxy was nice and the algorithm was well suited to the data, then this set will be small in size. But if p of xy was horrible, or if the algorithm was not well suited to the data, then this will still be correct. Okay, so you don't lose validity. It might be a larger set than what you would have hoped for, but it will always be correct. So in some sense, use your assumptions. Feel free to make assumptions and use them. Use them to design an algorithm to help you out. But the guarantee that I want should be true whether your assumptions were right or not, whether your model was good or not, whether your, whatever you thought held true, whether that was true or not, this will still be true. So in some sense, you should think about this as robustness to model misspecification. Okay, so it's robust to any assumptions you might want to impose. Yeah, so we're going to assume that this data is exchangeable. But for now, I've just stated it as this data is IID from a joint distribution, which is hence exchangeable.
But yet, what role the algorithm plays in the red stuff anyway?
Well,
you have to given xn plus 1, you have to give me an interval, right, or a set.
Yeah. So you're usually going to use an algorithm to come up with that set. So usually the algorithm, like if I give you a complex data set, a d-dimensional data set with a real number that you're trying to predict, how are you going to produce this set? What you're usually going to do is, I don't know what to do, I'll throw a random forest at it. This random forest is going to help predict y from x, and I will use the random the random forest to produce this underlying set. So the same way that you use a random forest to produce a point, you'll use a random forest to produce a set. So the point is that so there's going to be an underlying algorithm hidden there. That's what we use for predicting a point, and that's what we'll use to predict a set also. And so that's where the algorithm comes in. C, this set C will depend on the algorithm. It will depend on the size of the set C, will depend on the algorithm and on pxy. But the property that the set C will always be a correct prediction set will not depend on the algorithm and on the set and on p of xy. Sorry.
My algorithm always uses this. What if I have some ridiculous algorithm just always pops the same?
Yeah, so if you have a really bad algorithm, so for example, this is a valid algorithm. I take in x, and no matter what x is, I always output 0. That's my algorithm. The set C will still account for this. It will be a large set, and it will still be correct. So you can use a ridiculous algorithm, you'll get a large set C. You can use a very smart algorithm, you'll get a small set C. But no matter what algorithm you use, the set C that I output will have this probability. Okay? So in some sense, nature produces PXY. You give me your favorite algorithm, and I'll give you a set C that is correct. Okay? Yeah. Yeah, so think of it as 0.05, 5%. So you want a 95% confidence set. Alpha is just a confidence level that you're looking for. That's all. That's all it is. No. Alpha is just a fixed number like 5%. You just, if you do, you can ignore this alpha and read this as 0.95 if you want. That's it. Just.
If I want more and more accurate, less, if I wanted to reduce the uncertainty, does that the space of algorithms that I can explore will reduce?
No, you can choose any algorithm you want. You can choose any algorithm you want, and you can apply this, but you have to fix alpha. Pick an algorithm, fix alpha. Fix alpha at whatever confidence level you're looking for. You can ask for an 80% confidence set, a 90% confidence set, a 95% confidence set, a 99% confidence set. You can ask for those, but for now, let's say you're asking for just one of them. You're asking for a 95% confidence prediction interval. So the question is, if I want a 95% confidence in prediction interval, how do I produce it? How do I come up with it? Without making any assumptions about the algorithm that you're using or the underlying distribution, how do I come up with a correct prediction set? That's the question.
Sorry, but you said C depends on A.
The size of the set C depends on A. This property of the set C does not depend on A. Yes.
And if I knew everything about your A and everything about PXY,
Yes.
then I would be able to define C.
Yeah, that's right. So if there was an oracle, so you can ask what's the oracle thing to do. Let's say Y is real valued. If an oracle knew PXY exactly, then this set C would be the 1 minus alpha level set of the conditional distribution P of Y given X. No, I mean, an oracle doesn't need to look at an algorithm. The oracle knows the data set. For a new point xn plus 1, it'll look at what is the conditional distribution of y given xn plus 1 is equal to x, and it'll look at the 1 minus alpha level set, and that'll be the best interval you could possibly get. So for example, think of a case where y is independent of x. So let's say y is just normal 0, 1. Okay, it's just, there's no x, it just ignores x. For any x, y is just normal 0, 1. Then the best you can possibly do is predict minus 1.96 to plus 1.96. That's the best you can possibly do. And that's what an oracle would do. If an oracle knew that Pxy is just x is something and y is normal 0, 1, then the oracle would output this set as minus 1.96 to plus 1.96. But you're not an oracle, so you're going to have to do something else. So what you see is data, and you're going to use an algorithm to help you since you're not an oracle, and you're going to produce a different set. That's right. So I think Sandeep pointed that out earlier, that you can, if you output the script y, then this right hand side is equal to 1 and you're done. So yeah, so we're going to want, for example, an upper bound of like 1 minus alpha plus 1 over n or something of that kind also. That is, it's not over calibrated, it's exactly calibrated at 1 minus alpha. So we will want kind of an equality, but you'll see that with finite amount of data, there's always a 1 over n uncertainty. So what we will be able to achieve is 1 minus alpha plus 1 over n. That will be an upper bound. So that won't, I mean, the set, if I outputted the whole script y, there is a whole real line, then it's probability 1. But I'm looking for, and you'll see that all of these methods don't do that. They don't output the whole real line. They will output something with probability, basically 1 minus alpha. They will output a 1 minus alpha set. Yeah. Yes. 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 Exactly. Yeah. And you will use the same algorithm that you're already using. Like, you're not going to change the algorithm. The algorithm, for example, for a particular data set, if you thought a neural net worked well, you'll continue to use a neural net. I'm not going to change the way you train your algorithm or anything like that. So it's the same neural net. So for whatever your algorithm was, I'll tell you, don't just produce yn plus 1. Here's a set around yn plus 1 that you can use to So it's like a wrapper around any algorithm of your choice. Just like faced with a prediction problem in practice, you choose an algorithm. Somehow you choose an algorithm, right? And so I'm just going to say, okay, choose your algorithm, and I'm going to do a wrapper around that algorithm that doesn't produce just a point, but produces a set. And the set will satisfy this guarantee, no matter what algorithm you used and no matter what the underlying distributions are, it will be a correct prediction set. Yep.
There's an article which finds basically the volume of the content of the conditional distribution. Can you say that there is an
It's a level set, actually, 1 minus alpha level set. Yeah.
So, can you say there is an algorithm that gets arbitrarily close to it? And if there is, then is it possible to find such an algorithm?
Yeah, so we'll come back to this. Typically not. So we'll talk about impossibility results. Typically not. Yeah. Okay, so hopefully everyone's good with the goal, and I'm happy that there were questions because this is a new goal in some sense. Well, it's not new for the people working in this small subfield, but it's a new goal, and especially the fact that we are trying to get rid of any assumptions you make, meaning that whatever I present will apply to random forests and to boosting and to neural nets and everything. It will apply to those. There'll be practical algorithms that you can run tonight if you want to, simple algorithms that you can run. Okay, so we didn't think when I was getting into it and I was first presented with this, I didn't even think it was possible. Like, how can you do anything without any assumptions? Why should something even be possible? So that itself is surprising, which is, I guess, why this is a somewhat young area, is because maybe it was not realized that something like this is even possible. So we never shot for the stars because we thought the stars were impossible to reach. Okay, so this area started in about 2005 by a guy called Vladimir Vovk. He's a computer science professor at Royal Holloway, London, and he and several other co-authors have worked on this for 15 years, and they set the foundations for this whole area, and none of what I'm going to say would have been possible without their work on it. Now, the reason that, even though it's been around for 15 years, the reason it's not become popular is because the initial methods that they proposed were computationally infeasible. They were not even exponential time. They were basically infinite time, essentially. So they were theoretical constructs and not algorithms that you can actually run on a computer. But recently, in the last couple of years, we've been able to take his ideas and realize, oh, here are variants of those ideas which you can actually run. And so I think now it's actually practical. But he was the first one to realize that something like this was possible. He and his co-authors, Glenn Schaefer and several others. And so there's plenty of references I can point you to later, as well as in our papers on his work. Okay, so a few remarks are in order about this. So the first one is that we don't actually need the data to be IID from PXY. We just need them to be exchangeable. That is, these n+1 points need to be exchangeable. What does exchangeable mean? If you've not seen it before, it just means that where the probability distribution is invariant to permutations. Another way of thinking about that intuitively is which point is 1 and which point is 5 and which point is 20 doesn't matter. I could have relabeled them and the whole problem remains the same. So that's all I really need. I don't need IID data. I need exchangeable data, which is a weaker assumption. That's just a remark. For simplicity, you can think about IID data if you want to. The algorithm is optional. Like I didn't need the algorithm to define the problem, but often we use an algorithm for prediction, so it's useful to write it this way. And the algorithm actually is assumed to be permutation invariant, which means that it really takes in a set of data points, not in any order. It takes in a set. You can think about the first thing it does is it shuffles the set, whatever. It takes in a set. Doesn't depend on the order in which you presented it. So that's the assumption about the algorithm. It can be a randomized algorithm, that's fine. If it's a randomized algorithm, this probability is also over any randomness that the algorithm used. So, but it's an algorithm that doesn't use any ordering information in the data. As several people pointed out already, this requirement is trivial without any size or efficiency concern. So I can always output the set script y, and the right-hand side will be 1, and I'm done. But implicitly, we want something that's really 1 minus alpha and not 1. And so the question is, how do we do that? The next remark, as again, someone had asked in the question, so I guess all questions were on point. The probability is over all of the training data and the test data. So it's over n+1 data points. That's what this probability is over. And over any algorithm randomness if your algorithm was random. And most importantly, this statement is not conditional on xn+1. Okay, so this is marginal over xn+1, not conditional on xn+1. So because I think that's particularly important, I have a separate slide just for this. Okay, so there's a difference between marginal coverage and conditional coverage. And conditional coverage is impossible, so we can prove that. So here, let me state the differences. So the first, this is what we're aiming for, where this probability is over all n plus 1 points. This is not what we're aiming for. I could have aimed for this. So what is this? For all x, the probability that yn plus 1 is in C of xn plus 1 conditioned on xn plus 1 equal to x, this probability is at least 1 minus alpha. This is a conditional probability taken over the n data points and p of y given x for the n plus first data point, but not px for the, so it's like just, it's conditional on xn plus 1. That, and this statement is basically taking this and taking an expectation over xn plus 1 also. Okay, and so essentially we are not aiming for this, we're aiming for this. It's a small but super critical difference. And essentially you can prove, and recently several authors have proved that assumption-free conditional inference is impossible. So this statement, getting this without assumptions is impossible, meaning that you can come up with distributions pxy for which the volume of this set must necessarily be infinite. If you want it to be correct conditionally, you must have an infinite size set. So you can prove this. So this statement is impossible, so we're not going to aim for it. We're going to aim for this statement. I mean, the fact that this statement is itself achievable without assumptions is remarkable, but this would be even better, and we can't get that. And, oops, there was, okay, that's it. Okay, so that's all I have to say. Any questions about the goal? Marginal assumption-free predictive inference, not conditional assumption-free predictive inference. Okay. Excellent. So let's look at some methods for assumption-free predictive inference. So this is, I'm going to go in a different chronological order. And the reason is simple. The original works, as I said, by Vovk and others, they were computationally infeasible, and they require like some real thought process, some imagination. So they're little more subtle, and so I will not present them first. I'll present them second. Okay, even though historically they're first. What I'll present first is a very, very, very simple method that in some sense is it's really what one should simply do in practice. If you're faced with a problem, this is the method that I would use in practice. Okay, so it's called split conformal prediction. Now, data splitting is somehow an underappreciated idea, and so this is what we're going to do. It's extremely simple. I can describe it on one slide visually. Okay, so I'm going to split my data into two parts, D1 and D2. Okay. I'm going to use D1 to train my prediction algorithm, and I'm going to use that to get my predictor A. Okay, so maybe you trained a random forest on it, and that's your predictor A. Now on D2, what I'm going to do is I'm going to calculate holdout scores. Okay, so these are, for example, if your Y values were real, then you would calculate a residual of this kind, where Yi minus, this is your prediction A of Xi, that's your residual Ri. But it does not need to be in this form if Y is not real valued, or even if it is real valued, you don't need to choose this score. You just choose some score, whatever your score is. I'm just going to write it as, using the algorithm, I will see how well this algorithm is able to predict on held out data. How good is it on held out data? We do this all the time. This is just a held out score. I'm going to call that Ri. Okay, so A is now fixed. A was trained on the first half. I'm evaluating the holdout scores on the second half of the data. Okay, so let R bar denote all of the residuals on D2. Okay, A is trained on D1, scores are calculated on D2. All right. Now, I'm just going to use this notation Q1 minus alpha of R bar. Okay, now R bar, like these are just real values. Okay, so you have N2 data points, and I have N2 real values, one for each data point. So I'm going to sort them, and I'm going to take the 1 minus alpha quantile. Okay, that's the 1 minus alpha quantile of these guys. I'm going to just denote that by Q1 minus alpha of R bar. Okay, so for example, these could be 0.3, 0.8, 0.1, 1, 3, 80, 20, something like that. I'm going to sort them and look at what's the 95th percentile, and let's say it's 22, and that's Q1 minus alpha of R bar is going to be 22. Okay, that's what it is. Now this is my prediction set. I'm going to use my predictor A, trained on the first half, to produce the prediction A of xn plus 1. And I'm going to use the calibration from the second half and add and subtract Q1 minus alpha of R bar. Okay, so I'm giving it for the real valued case. I can write it down for the more general case, but for now, think about this as a real valued case. It produces an interval. This interval is centered at a of xn plus 1, your prediction, which you would have made anyway. If I didn't give this talk, you would have output this. And all I'm saying is output this plus or minus a 1 minus alpha quantile of held out residuals. Okay, and then this is the theorem. This fact is just true without any assumptions on x, y, algorithm, what this algorithm is doing, nothing. Without any assumptions, the probability that yn plus 1 is in this set is at least 1 minus alpha. No, the sizes of the sets don't have to be equal. You could have split it into two sets of any size. That's fine. Because the data was exchangeable, you don't even have to do a random split, but it helps to think about it as a random split. Okay, so hopefully all of you will agree that this is a very simple method, right? Split your data in two parts, train on one half, calibrate on the other half. We often call this, in this area, we call this the calibration set. So training set, calibration set. And so this is used to calibrate how well am I doing out of sample. That's all it's used to calibrate that. I use the 1 minus alpha quantile and I get this for free. Yep. Yeah, no, not for predict. Yeah, I'll come back to this later, but not for predictive inference. Yeah. Yeah. That's right. That's right. Yeah.
And the question is that is there a value of, let's say, also adapting that ball, so to speak?
Yeah. So you can. Yeah.
So I need to interpret that. So in some sense, the residuals themselves are kind of labels, or the X is being your features.
Yeah.
So there is a value to sort of kind of not bootstrapping standard sense, but apply some kind of supervised learning.
Yeah, and we'll come to this later. That actually comes in your choice of predictor. In some sense, instead of using a random forest, I would use a conditional random forest or a quantile random forest, which makes uses different predictions in different parts of the space. And yeah, but we'll come to that. That's actually, it comes up in the choice of the predictor. But yeah, I mean, good question. Yeah. Yes. Because I assume that the data is exchangeable. So in some sense, it's already, I've already permuted the data. That's all I meant. Yeah.
So we can't comment about the size of D1 and
Sorry?
can we comment about the sizes of D1 and D2?
I mean, this statement is going to be true irrespective of any sizes of D1 and D2. But you can think, the simplest thing is to do a 50-50 split. I mean, that's the simplest thing. But if you chose to do a 40-60 split, that's fine. If you chose to do a 60-40 split, that's fine. And you can try and understand what are the differences, like what are the pros and cons of each. Essentially, so imagine that you use 99% of the data for this and 1% of the data for this. What's going to happen is that A will be extremely, well trained, very accurate. That's great. Hopefully, if you used a good prediction algorithm. But the 1 minus alpha quantile, you'll have very few points to find the 1 minus alpha quantile. So let's say you had only 10 points. So the 1 minus alpha quantile will be the 10th one, which is the largest of the held out residuals, and that's just it'll be a larger set than you need to, just because you left too little data for calibration. Now the reverse problem can occur. If I used only 1% of the data for training and 99% to calibrate, then maybe I'm only training on 100 data points, but I'm calibrating on 10,000 data points. Then maybe your algorithm is really bad, so the held out residuals will be very large, and so the 1 minus alpha quantile of the held out residuals will also be very large, and that's not good. So in some sense, there's a balance between how much data you use to train and how much data you use to calibrate, and typically 50-50 or 60-40, 40-60, those kinds of things will work well. But 99-1, 199, while this statement will be true for any split, this set will be very large if you did a very uneven split. Then the set will be larger than it needs to be. Yeah, exactly. Yeah, that's a good question. And maybe I should just say that this was proposed last year by my colleagues at CMU, Jing Lei, Larry Wasserman, Alessandro Rinaldo, and Ryan Tipshirani. And an important thing maybe coming to what you were saying is you can prove that the size of the set is also at most 1 minus alpha plus 1 over n2 plus 1. So that n2 is the size of that set. So imagine that let's say you have 10,000 data points. Then essentially you say you use 5,000 for training, 5,000 for calibration. Then you ask for a 95% interval. You basically get a 95% interval. Maybe it's 95.1%, but it's a 95 point something, really close to 95% interval, as close as you can get with the discreteness of having n points. But if n is reasonably large, you ask for 95%, you get 95%. You don't get 100% or 99.5% or something like that. Okay. No, that's just because of the quantile that I calculated was based on n2. Okay, this is just the coverage. This is the probability content does not depend on n1. The width of this interval depends on n1. The width, how large is it? That's not what this is saying. You might want to prove an additional statement of what is the width of this interval is just 2 times the 1 minus alpha quantile of R bar. That's the width of the interval. Proving anything about that without assumptions is impossible. Because if you have a very heavy-tailed distribution, then the 1 minus alpha quantile will be large. For a light-tailed distribution, it will be small. So you cannot prove, in any assumption-free fashion, you cannot prove anything about the length of this interval, but you can prove something about the probability content of that interval. And so this interval will automatically be small if it's a light-tailed distribution and things are nice. It'll automatically be large if it's a heavy-tailed distribution and so on. It'll always have 95% coverage if you ask for it. Yeah. Sorry. No, for as long as n1 and n2 are greater than 1. I need to have at least 1 point. Yes, then it's true. But if you want it to be meaningful, then I guess 1 over n2 plus 1 should be at least, so that this shouldn't be 1 essentially. So, yeah. So but it's correct. Mathematically, the statement is correct for any n1 and n2 greater than 1. But practically, you want it to be at least 100 or something like that. Yeah. No. Yeah. Yeah. So you can't. Yeah, you can't. You can't say. In general, you can't say. Yeah.
Is there any value to the logic that if alpha is alpha by 2, take 2 subsets and take a negative over 2?
Yeah, that's actually what you would do if you have 2 algorithms and you're like, I'm not sure, linear regression versus deep net, what should I do? Well, take alpha by 2 and alpha by 2 and take their intersection by Bonferroni, you get a 1 minus alpha set. That's also correct. So now once you know how to construct 1, you can construct multiple take intersections using Bonferroni. That's fine. That's totally valid. Yes. Can we find limits on C? What does that mean? What does that mean? What do you mean by limits?
How large or how small it could be when it is just given to you.
Yeah, not in any assumption-free sense. Like, imagine X could be crazy, crazy distribution. Y given X could be a mixture of a Cauchy and a Gaussian. So yeah, with an A, the algorithm A could be ridiculous, right? You can imagine the algorithm A is a deep net trained for some time, followed by a random forest. It just could be some weird algorithm. Yeah. Yeah, I don't think you can say anything in general. Yeah, maybe for a specific case you might be able to, but there won't be any assumption-free statement. Yeah, maybe you can find something tailored to your situation, but this statement is tailored to any situation. Yep. Nothing. No. There's no assumption at all on A. A could be the predictor, take in X and output 0. That could be the predictor. It's fine. A could be linear regression, A could be neural net, A could be anything. In fact, like A is remember the prediction algorithm A, it took in a data set of any size. So here is actually a valid algorithm A. If the data set is size 3, use nearest neighbors. If the data set is size 4, use linear regression. If the data set is size 5, use quadratic regression. If the data set is size 6, use a random forest. That also is a valid algorithm. It does something crazy. I mean, why would you ever use that? But this statement will still be true. So I'm not making any assumption on it. Definitely not that it fits the training data perfectly. Nothing of that kind. I mean, it will also apply to a predictor that fits the training data perfectly, but that's not an assumption. Yeah, exactly. Yeah. Okay, so yes. Yeah. So essentially what's going on over here is that this statement holds true on average over xn plus 1 drawn from that distribution. What it basically means is that in some part of the space, I might undercover. In some other part of the space, I might overcover. But on average, overall, over draws from the space, I will get 95%. So I cannot guarantee that at every single point in the space, I get 1 minus alpha. What I can say is on average over points in the space, average taken according to px, I will get 95% coverage, but not, that's the difference between conditional and marginal. True at every point or true on average. Okay. All good? Great. So here's, because this is such a simple method that works without assumptions, when you don't make assumptions, the theorem statement can't be, the proof can't be complicated because you don't have any assumptions to play with. So the only assumptions I can use are that the data is exchangeable and nothing else. And so the proof is actually just one line. So I'll present the proof. So here I'm just recapping. For each point in D2, I calculate a residual. I calculate this as the confidence, my confidence set. Now I'm going to rewrite this set for the proof. I'm going to rewrite it in this fashion. Okay, it's the set of all y such that y minus a of xn plus 1 is at most the 1 minus alpha quantile. Okay, so everything that's close enough. So a of xn plus 1 is my mean prediction. Everything that's close enough to my mean prediction is fine. So if the distance from my mean prediction is small, that's fine. That's included in the set. If it's too far from my mean prediction, that's not in the set. That's just a rewriting of this statement. Okay. So this was the claim that was made. So here's the proof. I've only left this much space for the proof, which means it's short. Okay. So here's the proof. So now the claim is that yn plus 1 lies in this set. So the way you have to imagine it is that xn plus 1, yn plus 1 was drawn from this distribution and yn plus 1 was hidden from you. I just didn't show it to you, but it's there. So theoretically, I can imagine calculating Rn plus 1. This is the proof. So I don't know yn plus 1, but I could calculate it. So it's just yn plus 1 minus a of xn plus 1. That's what Rn plus 1 is. And because all of the data points were exchangeable from the point of the view of the algorithm A was trained on the first half of the data. From the point of view of that algorithm A, all of these N2 points and the new point are all exchangeable. There's no difference between the N2 points I didn't see and the N plus first point. There's no difference between them. So these residuals are exchangeable, where this residual is calculated using yn plus 1 that I don't know. For the proof, these residuals are exchangeable. So what does that mean? It means that the rank of the n plus first residual is uniform among all of these. Okay, so the probability that Rn plus 1 is the largest or the smallest or the third biggest or the fifth biggest, they're all equally likely. The rank of Rn plus 1 is just uniform because all of these points were just exchangeable anyway. And hence, we see that an error occurs, which means that yn plus 1 is not in this set. I make a mistake. Yn plus 1 is not in this set if the distance between yn plus 1 and a of xn plus 1 is larger than q1 minus alpha. If the distance is large, it's not included, it's not in the set. So I make an error if I put yn plus 1 over here, this is just Rn plus 1. So an error occurs if Rn plus 1 is too large. If the n plus first residual was abnormally large, then I make an error. Specifically, if the n plus first residual was larger than 95% of the held out residuals, then I'll make an error. But the probability that this happens is at most alpha because the rank of Rn plus 1 is uniform. So it's equally likely to be any rank. What's the likelihood that it's its rank is more than 0.95. It's at most 0.05. Okay, so it's okay if you didn't get the proof. You can dwell on it later on, but it's really trivial. The proof is trivial. The rank of Rn plus 1. So these are real numbers. I sort those real numbers, and I ask which position does Rn plus 1 occur among those. And because those are exchangeable, the position at which Rn plus 1 occurs is a discrete uniform distribution over n2 plus 1 points. And so that's also actually why you get the reason you get the upper bound is also because these are just n2 plus 1 points, and the rank of Rn plus 1 is, well, it's at least 1 minus alpha and at most 1 minus alpha plus 1 over n2 plus 1. So this probability is also, it happens with probability at most alpha, but it also happens with probability at least alpha plus 1 minus n2 plus 1. Anyway, short proof, you can think about it later on. Let's move. So here's an example of applying this in practice in a simple situation. So here I'm using for visualization, it's a univariate x and a univariate y. Okay, and the gray circles are my input data. So as you can see in this case, the input data is heteroscedastic. Okay, which means that it has different amount of noise here and different amount of noise here. So in some sense, you can think about the red line is like the true mean, you can say, if you want, you can think about it as true mean. And the amount of noise depends on x. So maybe you can imagine y is sine x plus normal 0x. So it's a zero mean noise, but the variance is small on the left end and the variance is large on the right end. Okay, so it's just some model I'm using to show you what the data looks like. So now I train using something like quadratic regression or something. The algorithm I use is quadratic regression. And in pink, what you're seeing is the conformal band produced at each point. So I can what I'm plotting over here is actually in red is the mean prediction at each point. That's just the regression algorithm output. It outputs a function, so that's the function, the output of quadratic regression. And what I did was for every point, I just calculated what would my split conformal have output at each point. Okay, so I can ask at this point, it's just centered at a of xn plus 1 plus or minus a 1 minus alpha quantile. And so at every point, it's just the mean prediction plus or minus a 1 minus alpha quantile. So this red band is the prediction band produced by split conformal. And the reason I